Hello everyone, in the last class we discussed about equivalent static method for estimation of design seismic load. We also distributed the estimated design seismic load across different floors to obtain design floor forces, which was then used to obtain a story shear, and the story shear was distributed among various lateral load resisting systems or elements of that story. Today we will illustrate the same through an example problem. Before we get into the example problem, let us summarize what were the steps involved in the equivalent static method. The first step was the determination of total design lateral force for the building, which was based on code estimated fundamental period of the building. We also looked into these expressions in the last class. Once we have the total design lateral force for the building known to us, we shall distribute the same vertically across various floor levels. Now, this is based on a simple code formula and appropriate only for regular buildings. In fact, equivalent static method itself is appropriate only for regular buildings which have height less than 15 meters in zone 2. Now, this simple code formula is based on the seismic weight of various floors and height of various floors measured from the base. After obtaining the design floor forces, we shall obtain the story shears in various stories and then distribute those into or among various lateral load resisting elements based on floor diaphragm action. We have seen that if our slab is able to provide a rigid diaphragm action, we distribute the force in proportion to the stiffness of various lateral load resisting elements, which are columns and shear walls. If the slab is not able to provide rigid diaphragm action or the diaphragm action is flexible in nature, in that case we have to consider the flexibility of the diaphragm. However, many global codes also suggest that the distribution can be done in proportion to the tributary area in that case. We have also seen how do we classify our slab action, that whether it is a rigid diaphragm action or a flexible diaphragm action. Now, once we have this understanding, now let us get into the example problem. So, here we are supposed to design a 3-story hospital building which is to be constructed on a hard soil site in New Delhi, for which we need to estimate the design seismic load. In this case, the building comprises of reinforced concrete special moment resisting frames, that is SMRF, in the orthogonal direction, that is we have SMRF in direction x as well as direction y. The plan and elevation details are shown over here. This is the plan, this is the elevation, and our slabs are monolithically cast with the beams. The slabs have thickness of 125 millimeters. The beams have cross section of 250 millimeter by 350 millimeter. The columns have cross section of 250 mm by 400 mm as shown over here. So, you can see that this dimension will be 400 mm and this dimension will be 250 mm. Okay. There are two types of walls. All these external walls are 250 mm thick and these internal walls are 150 mm thick respectively. The live load on the floors is estimated as 3.5 kilonewton per square meter on these floors. Obviously, while calculating the seismic weight, you may ignore the live load on the roof, that is as per IS 1893 part 1 2016. You are well aware of that. You can always look into the code as well. Now, once we have this understanding, let us make some assumptions. We do not have any parapet wall on the roof, which means there is no loading coming from parapet wall. So, now we have to use equivalent static method to determine the design lateral force on the highlighted internal frame. We have to find out the design seismic load only on this very frame. which is an internal frame, and then distribute it along the building height. You can assume the grade of concrete to be used as M25 and steel to be of Fe415 grade respectively. The unit weight of reinforced concrete and masonry infill can be taken as 25 and 20 kilonewton per meter cube respectively. Now, let us get into how to solve this problem. When we are trying to solve this problem, the first thing should be how do we calculate the seismic weight of the building. So, let us illustrate that. For calculating seismic weight of the building, we can understand that it will be same for first and second floor. However, it will be different at the roof level. Why? There are multiple reasons. First of all, the dead load coming from walls, which is taken as tributary area, that is in a case of any story, it shall be half shall go to the lower floor and half shall go to the upper floor. So, for the roof, you do not have any loading coming from top in this case. Alright, so that is one difference which makes your seismic weight of this roof different. The second difference is that for roof level, you can ignore the contribution of live load. Now, for roof level, the second difference is that for roof level, you can ignore the contribution of live load to the seismic weight of the building. Therefore, we shall calculate the seismic weight of these two floors together, and the seismic weight of the roof level shall be calculated separately. So, the seismic weight at the first and second floor levels, let us first calculate the self weight of the slab. Now, for that frame into consideration, the self weight shall be 0.125, which is the thickness of the slab. 8 meters is the width of the frame into 5, that is 5 meter, which is the tributary area on this very frame. So, this is the area that we shall be considering. So, it is 8 into 5 multiplied with 25, which is the unit weight of reinforced concrete. So, it gives us the self weight of slab to be 125 kilonewton. The self weight of beams are then calculated. Here we will have how many beams? 2 beams which will have length of 4 meters each in the frame itself, and from the transverse frame you will have self weight of the beam coming into picture of half beam on either side. There will be 6 such beams actually, which will have length of 2.5 meters, or you can say 3 into 5. So, this is the way how we have estimated. The cross section of all the beams are given to be 250 mm by 350 mm, and then when multiplied with unit weight of reinforced concrete, we get the self weight of beams as 50.3 kilonewton. For columns, we shall consider the tributary area, which means for first and second floor levels, you will take into account half of the column from below and half column from above, which means we have to take one column height only. So, the column has a dimension of 250 mm by 400 mm, and then 3.5 meter is the story height, then multiplied by 3y3, because in this frame there are 3 columns, multiplied with the unit weight of reinforced concrete, we get the self weight of column as 26.25 kilonewton. What shall be the self weight of infill walls? So, in this case you would realize that the frame has all the inner walls, but at the two ends of the frame you have external walls in the transverse direction. So, based on the tributary area, you can consider that. You can pause the video and look into the detail of this, or you can calculate on your own as well. Here the unit weight of masonry shall be used, that is 20 kilonewton per meter cube. So, we shall obtain the self weight of infill wall as 311.5 kilonewton. Now, if we add all these self weights, we shall be able to find the total dead load at first floor level or the second floor level. So, which comes to be 513 kilonewton roughly. Now, at this point, since the live load is given to be 3.5 kilonewton per meter square, so 50% of the live load contribution shall be considered in case of seismic load calculation. So, the live load at first and second floor levels shall be 3.5, which is the loading intensity, into 8 into 5, which is the tributary area for the frame, multiplied with 0.50, which is the contribution of live load in our case. This gives live load at the first floor or the second floor level to be 70 kilonewton. Now, if you add the total dead load and this contribution of live load, then we shall get the seismic weight of the floor. So, the seismic weight at first and second floor levels W1 and W2 are calculated at 583 kilonewton, and then let us calculate the seismic weight at the roof level. So, for calculating the seismic weight at the roof level, what shall be the change? The slab will remain the same, the beams will also remain the same, the columns will be halved actually, because beyond the roof level there is no column. So, only half column from below shall be taken into consideration as the lumped mass at that location. The cell weight of infill wall will definitely change, it will be halved as well. Then the sum, that is the total dead load, will be calculated and the live load contribution may be ignored. Let us look into that. So, the cell weight of the slab and beams remain the same as expected, while the cell weight of columns and infill walls were reduced to half, as in the case of seismic weight at first and second floor levels. So, now the total dead load at the roof level becomes a sum of all these to obtain 344 kilonewton respectively, approximately. Now, the live load at the roof level is ignored, therefore, the seismic weight at the roof level shall be equal to the dead load, which we have calculated as 344.19 kilonewton. Now, the total seismic weight of the frame shall be calculated as sum of W1, W2 and W3. What are W1 and W2? Those are seismic weight of the first and second floor levels. W3 is the seismic weight at the roof level. So, upon finding the sum, we get the total seismic weight of the frame as 1510.3 kilonewton. Now, once we have found out the seismic weight of the frame as well as for different floors of the frame, we shall now find out various components or factors that were involved in calculation of AH. So, for calculation of AH, one very important thing was determination of SA by G, which represents the hazard at the site. So, for SA by G, what do you need? You need to know the natural period of the building, you need to know the soil type at the site. So, in this case, we are given the hard soil site, but we are in need of the natural period of the building. So, for calculating the natural period of the building, in this case, since our building is comprising of reinforced concrete moment resisting frame building, we can have two different cases. If we ignore effect of masonry infill, that is, we are considering only the framed building, then in that case the natural period shall be given by this expression. If we consider the effect of masonry infill, then in that case this is the expression. Here h is the height of the floor from the base of the building, d is the dimension which is in the direction of the earthquake, the planned dimension of the building in the direction of the earthquake considered. So, ignoring effect of masonry infill, we get the value of natural period of the building at 0.4375 seconds, and for considering effect of masonry infill, the natural period is found to be 0.334 seconds. Now, based on these values of natural period as well as knowledge of the underlying soil media, that is the hard soil site, we shall enter this very plot of SA by G versus natural period, and from there we shall be able to say that if we ignore the effect of masonry infill, the value of SA by G shall be equal to 2.286. If we consider the effect of masonry infill, then the value of SA by G shall be calculated as 2.5. Now, once we have the information about SA by G known to us, we shall calculate the other factors, which were your seismic zone factor Z, importance factor I, and response reaction factor R. So, let us calculate that. Since our building is supposed to be constructed at New Delhi, which is located in seismic zone 4, the zone factor shall be equal to 0.24. We have already seen the values of zone factor in the last class, or you can always go to various tables which are mentioned over here in the slide in order to understand or find out what shall be the value of these factors, whether it is zone factor or importance factor or response reaction factor. Since it is a hospital building, the importance factor shall be taken as 1.5, and since the building comprises of reinforced concrete special moment resisting frame system, the response reaction factor can be taken as 5. So, had it been an OMRF, ordinary moment resisting frame, which means that if you do not consider the ductile detailing guidelines, then in that case the response reaction factor would have been just 3. Now, once we have all these values known to us, let us calculate the design lateral force or base shear. So, again two cases, ignoring effect of masonry infill, that is considering only bare RC MRF building, and the second case is considering effect of masonry infill. So, upon substituting the values, we get value of 124.29 kilonewton for the case of ignoring effect of masonry infill, and for the case of considering effect of masonry infill, the design base shear is equal to 135.93 kilonewton. Now, you would recall that in the last class we have discussed about the minimum value of design base shear stipulated by our code IS 1893 part 1 2016. In that case, for zone 4, the minimum design base shear shall be equal to 1.6% of the seismic weight of the building. So, which is coming to be 24.16 kilonewton in the case of ignoring effect of masonry infill, and in the case of considering effect of these masonry infill, we are getting value of 24.16 again, which is lower than these two, and therefore these values which we have calculated, which are shown in bold over here, shall be adequate. Now, once we have the design lateral force or the design base shear known to us, we shall distribute it among various floors. So, for distributing it vertically, that is across various floors, the expression is given over here. So, it means that the base shear is distributed in the proportion of WH square. Now, in this case, again we have considered two different cases, ignoring effect of masonry infill and considering effect of masonry infill. So, what we have obtained, that the first floor level shall attract a force of 12 kilonewton roughly if the effect of masonry infill is ignored. At the same time, if the masonry infill effect is considered, then in that case that force at the first floor level shall be 13.18 kilonewton, and so on. So, let us show it through a schematic diagram. So, on a schematic diagram, as we can see that the first floor level forces, which is 13.18 kilonewton, the second floor level force is 52.72 kilonewton, and the roof level, the floor force is equal to 70.03 kilonewton. Now, if we start summing up the forces from above to below, then what you will find that becomes your story shear. For example, the story shear in the top story shall be equal to 70.03 kilonewton, because then only there will be a force equilibrium. For the second floor, it shall be equal to 70.03 plus 52.72 kilonewton, which is 122.75 kilonewton, and then for finding the stress shear in the ground floor, you end up adding 13.18 kilonewton load as well. Now in our case, the slabs and beams are monolithically cast. The slab exhibits rigid diaphragm action. Since there is a rigid diaphragm action, the distribution of stress shear will be done in proportion to the stiffness of the various lateral load resisting systems. So in this case, we have three columns which have exactly similar cross section and they also exhibit similar stiffness. Therefore, the stress shear is divided equally among these three columns. Now for this you can refer to this very clause in IS 1893 part 1 2016. As we have understood or looked into the equivalent static method for estimation of design seismic load, we have understood that the magnitude of lateral force depends on estimated fundamental period and the distribution along building height is based on simple formulae which are appropriate only for buildings with regular distribution of mass and stiffness. However, as we proceed our discussion over next classes, where we will learn about dynamic analysis method, we will understand that the magnitude of lateral force depends on natural vibration modes and thereby also on the distribution of mass and stiffness over height. We shall look into two different dynamic analysis methods, which are response spectrum method and response history method. These methods share similar capabilities and similar limitations as equivalent static method. However, there is a slight difference that the dynamic analysis method is able to capture various natural vibration modes. However, the equivalent static method ignores any other natural vibration mode. It gives just a fundamental natural period. Okay, having understood all of these, in the upcoming classes we will look about dynamic analysis methods. Thank you.